Hello everyone, and welcome to a discussion of force and acceleration for objects moving in a circle at constant speed, otherwise known as uniform circular motion. Now, we've already partially discussed force and acceleration. I mean, we have their magnitudes, right? We already know that the net force required to make something move in UCM is equal to mv squared over r, mass times speed squared divided by the radius. And we know that the resulting acceleration has a magnitude of speed squared over the radius, v squared over r. But if we want to completely describe the force and the acceleration, we also need directions, because after all, force and acceleration are vector quantities. So let's start out by trying to decide what direction the force acts on an object moving in a circle at constant speed. Here we have a top-down view, if you will, looking at like an eraser being strung on the end of a on the end of a string. Right, so it's just going in a nice slow horizontal circle, and we're looking down on it. And I want to know about what direction does the force act. Well, first off, realize that there does have to be a force. Right? We know there has to be a force, not only because it was in the simulation, but because, after all, we know from the ideas of Galileo and Isaac Newton that objects tend to just move in straight lines on their own, right? They have inertia, they have a tendency to just keep moving the way they were moving, and in order to change something's motion, you have to have a net force acting on it, right? And changing that motion could be speeding up, slowing down, or changing its direction. So something moving in a circle, right, doesn't naturally move that way, right, unless there's a net force applied. But what is the direction? Well, let's think about how Newton saw this. A little simulation I picked up, and it's how Newton thought of circular motion. Okay? So, watch this little ball go here. And every time it hits the wall, it gets a force put on it. That's that purple arrow, right? It's a force put on it. Now, right now, it's moving in a square, right? But if we change the number of times it hits the wall, notice there's still these little forces being put on it every time it hits the wall, right? It's looking more like a circle. If we have more little forces put on, it looks even more like a circle. More times hitting the wall, more forces, even more like a circle. That's as high as the simulation goes, is 16 times every time around once. But if we take this to kind of a calculus-y idea then, that if we wanted it to actually move in a circle, we essentially would need to apply that force constantly, all the time, right? We'd have to hit it at it constantly in order to get it to move in a perfect circle, right? So this is how Newton thought of why things would move in a circle. And if you saw those purple arrows, you might have an idea of the direction. But to help us out a little bit, let's look at a real-life situation like this that you saw in the IVV. Watch the video here. Took this right out of the IVV. So here's the professor, and notice where he's hitting the ball and what direction he's hitting the bowling ball to keep it moving in the circle inscribed on the floor. Do you see what direction he's hitting? Right, look at it here. He's not hitting forwards. He's not hitting backwards. He's hitting on the outside of the ball towards the center of the circle. Here, this one's the really good view of it. See what he's doing? He's constantly hitting it towards the center. Right? It's a central force, which is the name of this unit, an inward directed force, if you will, right, that we need in order to make something move in a circle. Can't push forward, can't push back, have to push in, right, in order to make something move in a circle. Now, that has a special name in physics. It's called a centripetal force. Centripetal is Latin for center seeking. Centripetal. Okay? There might be another word that you've heard that's similar. We'll get to that in a little bit. This is centripetal, center seeking, usually denoted by a little c as a subscript on the force. This is the inward directed net force acting on an object moving in uniform circular motion, moving in a circle at a constant speed. Right? The magnitude of it is still mv squared over r, like we found in our lab. Right? But now we know that the direction is always inward or centrally directed. That's why we call this unit central force. Okay, those are the kinds of forces we need to have to make something move in a circle at a constant speed. Now, this terminology, a lot of physics teachers would love to get rid of. I would, really. If it just disappeared off the planet, I wouldn't have a problem with it. The reason we would like to get rid of it is it sometimes engenders some misconceptions. This is not a new force. Okay? This is not some, force we add to our list of normal, friction, gravity, spring forces, things like that. Okay? Tension. This is a name we give to any force or combination of forces that points inward, centrally directed, that makes something move in a circle at constant speed. You would never, ever write F sub c on a force diagram. Okay, so you just wouldn't put that on a force diagram. Right? Instead, these are forces that we've seen before. For example, with the eraser being whirled on the end of a string, the force that's pulling inward is a string, so it's tension. Right? Tension's pulling on it. It could be... let's say, you have the moon orbiting the Earth, right? Well, what keeps the moon from flying away in its inertial path? Gravity, right? So the force of gravity acts as the centripetal force. Sometimes it can even be combinations of forces. The net effect is an inward directed force. Right? And we'll see that more when we talk about things moving in vertical circles in a few days. Okay? So, again, this is just a name we give to any of our forces that we've already talked about, or combinations of forces that happen to point inward and make something move in a circle at a constant speed. So take a look at this little GIF that I got from the concept builder guy. So here's a trolley or something like that, right? A cart, if you will, and there's a ball on it, right? And so the ball wants to move inertially. Right? Well, if there's no force acting on it, that's exactly what it's going to do. So when the trolley turns to the left, the ball just keeps moving inertially along its straight line path. Right? In order for the ball to continue in the circular path of the trolley, we need a force to be applied. So let's say there's a little wall on the trolley. So notice if you look carefully, the ball gets moving and then it hits the wall. So when it hits the wall, the wall pushes in on the ball. Ball pushes outward on the wall pushes inward on the ball. It's a Newton's third law interaction, right? So the wall is providing the force that keeps the ball moving in a circle instead of going along its inertial path. Right? This might be like you in a passenger seat of a car. Right? That door's there. That door is going to push in on you, keeping you moving in the circle with the rest of the car. Otherwise, out you go, right? And you go off tangent to the circle. Okay? So this would be like a normal force in this case. Not a new force, but just whatever force pushes inward and keeps you moving in a circle. Now, you might remember that when we learned about forces and accelerations in Newton's second law, right, we learned that force and acceleration are always in the same direction. Right? Something accelerates in the direction that you're pushing on it, right? So that means if the force is inward directed, so is the acceleration. And hence we call that a centripetal acceleration, a center-seeking acceleration, A with a little subscript of C, right, which is inward directed acceleration for something moving in a circle at constant speed. It has a magnitude, as we found earlier, of speed squared divided by the radius, and a direction that's inward. Now that's constantly changing when something's moving in a circle, but at least you can, if you look at it at any particular point, you know that it's acting inward just like the force. So this is kind of a special acceleration, right? Which is why it's got a special symbol. Kind of like we used free fall acceleration, negative 9.8 meters per second every second. We gave it the symbol G. Right? This one isn't that special in that it's not just a particular number, even if you stay near the surface of the Earth, but we can calculate it, right? Only needing to know two things, the speed and the radius of the circle that it's moving in. So if this is a ball going around in a circle, right, its velocity is tangential. Right? The velocity is tangent to the circle, and it's constant, and the acceleration is inward directed. Right? So if we put this in motion, right, we can see that the acceleration always points inward. Do you see the velocity arrow kind of continually moving, turning inward? Yeah, it's not pointing inward, but look at how it's changing direction, right? It's changing direction inward. If you want a more mathematical way of approaching that, well, go back and look at the proof, right, that you had in the previous movie, okay, that we did of this. But this is kind of more conceptually why it has to be this way, okay? Why the acceleration has to be inward directed all the time. Tangential velocity, right? Inward directed acceleration. So you may have heard another phrase or another word that you might have thought I was going to use earlier, right? But it doesn't really mean the same thing. It's related, but not quite. It's called a centrifugal force. Centrifugal means center fleeing in Latin, all right? The fugal means fleeing. Center fleeing. We have centripetal, which means center seeking, right? Centrally directed. Well, rather than me just trying to convince you of this, I'm going to let somebody who you've probably watched some of these things back in your youth kind of explain it a little bit before I take a crack at it. Here you go. Watch this movie.
Right now, this ball is spinning around in a circle, and I'm pulling on the rope. If I let go of the rope, the ball stops going around in a circle and goes off in a straight line. That's because spinning things are always changing direction. Now, take a look at this. Here's a dot on a spinning disc. Now, if the disc is spinning this way, the dot starts out going in this direction. But a moment later, the disc is spun and the dot is going in this direction. You can tell it's changed because here's the original direction right here. Then a moment after that, the dot's going this way. And here's the original direction. See, the dot is constantly changing direction. In fact, every part of the disc is always changing direction. There's something pulling on every part of the disc all the time. Just the way the rope was pulling on the ball when I was spinning it over my head. That force that's pulling everything toward the center is called centripetal force. Centripetal force. Centripetal force. Center seeking. Seeking the middle. Centripetal force. Without centripetal force, the disc would fly apart in a cloud of dust. See, without centripetal force, spinning things wouldn't go around in a circle. No, they'd go crazy. When you're in a car going in a circle, the car is pushing on you. Yeah. As the car turns, part of the car, the seat belt, is holding you in. The car is exerting what we call a centripetal force, a force toward the center. So right now, the door is pushing you to the center, exerting a centripetal force. The car is pushing on you in a circle. See, so it feels like you're pushing on the door, but really, the door is pushing on you. The force that you feel pushing on the door is what we call centrifugal force. But in a way, there's no such thing. Centrifugal force is what we call a fictitious force, or not a real force. See, because really, the door is exerting a centripetal force, even though it feels like you're exerting a centrifugal force. If the door weren't pushing on you, well, then you'd go off in a straight line. Here. You okay? See, the door stopped exerting a centripetal force, so you fell right out. Okay. Well, I'll see you later.
This is going to be a spinning thing.
Spinning thing like the Earth is going around in a circle. And it's going around in almost a perfect circle around the sun. That's because there's a force pulling it toward the sun. That's gravity. It's a centripetal force toward the center. Centripetal force. And there's a centripetal force of gravity that's holding the Earth in a ball. If the Earth weren't being centripetally pulled in, well, it would fly off into space in a cloud of dust. Ha!
So, Love the little demo there with the driving the car in the circle and the dummy, right? Because that's really just a real live example of the GIF I was showing you earlier, yeah? But one thing I hope you picked up from that, you notice he called this force a fictitious force, right? Because it's not really there. There's nothing pushing outward, right, on that ball on the end of a string, right? There's a tension force pulling inward, but nothing's pushing it outward. And one of a good piece of evidence of that is where does it go when you release the string, right? If you cut the string or if you flipped a switch and turned off gravity or something, it wouldn't go straight out from the middle, right? It goes tangent to the circle because that's the direction it was going before. So it feels to you, if you're actually in the car, okay, it feels like you're pushing out on the door. Really, you're just trying to go straight because of your own inertia, and the door is pushing in on you. Right? So it's a feeling more than it's actually a real force, which is why after this, you won't really hear me bring it up at all. Okay, especially because we tend to do these problems as if we're standing outside watching something be swung around. We generally don't do a lot of problems where you're actually in there. You know, sometimes we're driving in cars and things, right? But usually it's a little bit easier to realize that there's nothing pulling outward on you in those cases. One more movie for you to watch here. This one has a good demo in it.
Park you visit, the ride with the longest line is usually the roller coaster. Most agree that the scariest part is when you find yourself upside down inside a loop. You might feel more secure knowing that it's not just the safety belt that keeps you from falling off your seat. It's also the laws of physics.
We're going to see how physics relates to a roller coaster. One of the most important principles in force on a roller coaster is that it's centripetal force. What does this glass of water have to do with centripetal force anyway? Let's find out. We have Arvin back here, has a board attached with some strings and place this cup of water, regular water, on the board. And all Arvin has to do is take that cup of water and swing it around his head just like this. And if you have enough belief in physics and centripetal force, you know it can't possibly come off. Right, Arvin? All right, Arvin, let's see if you make it over the top. Who thinks Arvin can make it? 1, 2, about 5. All right, Arvin's building up his confidence now. All right, go for it. Over the top. Now, do you know how to stop? Whoa! Well, so on a roller coaster, you get into a loop, you're at the very top. What's happening is the track is pushing which way? Down. Well, that's strange. You're being pressed into your seat even though you're upside down. Did y'all feel upside down when you're upside down? Yes. Did you ever leave your seat? No. You never left your seat. The same as the cup never leaves the board.
Centripetal force is simply the force that makes an object moving in a curved path keep turning as it goes. The track, together with gravity, provides the centripetal force needed to keep a roller coaster car turning. When a roller coaster car moves through a loop that you can think of as part of a circle, it requires centripetal force pushing toward the center of the circle to continuously change the direction of the car.
On the Draken fire.
When Professor Wright swings the cup of water on the board, the centripetal force is supplied by the tension of the string, which applies enough force on the board so that the board makes the cup continuously change direction toward the center of the circle.
On a roller coaster, first you go up the top, and you come down like this, right? And the water doesn't leave.
At the very top of the circle, gravity plays the role of centripetal force too, acting with the string to keep the cup turning as it moves along its curved path.
All right, now stop it.
When you're high off the ground and upside down in your seat, you expect to fall down because gravity is pulling on you. Instead, you feel as if you are being pushed into your seat. To understand this, you have to imagine something really scary that could never happen. Imagine that as you just started upward into the loop, the roller coaster car, the seat, and the seatbelt just appeared. You would continue flying along as if you were launched from a cannon until gravity pulled you back to Earth. The roller coaster is designed so that this imaginary path goes higher than the roller coaster loop does in reality. To stay in the loop, you need centripetal force pushing on you to make you turn more sharply downward. The track, together with gravity, provides the centripetal force that pushes down on the car and in turn on your seat and on you. So when you feel pressed into your seat, the seat is also pushing down on you to keep you from going higher than the track. Next time you're speeding through a loop, you'll know that it isn't just the safety belt that keeps you from falling out of your seat. It's also the laws of physics.
So I'm going to show you an actual demo of, swinging a bucket with water in it around and around eventually. But just to summarize what you've hopefully gotten out of this video, right? Something that is going to move in uniform circular motion needs to have a force acting on it. That force has magnitude mv squared over r, or net force if it's a combination of forces. Right? Mv squared over r is the magnitude, and the direction is inward, right? Centrally directed. And therefore the acceleration, which has a magnitude of speed squared over the radius, is also centrally directed. And hence they're both called centripetal if you want to use the old language. Right? No such thing as centrifugal, right? Just a centripetal inward directed net force, which can be provided by any of the forces that we have discussed in the past. Right, so now we're going to start deploying this idea on some horizontal circles and things, and then eventually we'll move into vertical circles.